This is Gatoino, the best cat laser toy that's not for sale in stores. It's made from a combination of 3D printed parts, off-the-shelf electronics, a custom PCB and controlled by an Arduino Nano with custom software. It features an OLED display for quick and easy setup. The development took me years, from the first prototype hanging from the ceiling to a convenient form factor you can put on a shelf or even stick to the wall. Everything along the way has been tested by a small team of feline experts for maximum satisfaction. And since every movement is random, playing with it never gets boring. Unfortunately, you can't buy it anywhere, but you might be able to build one yourself. More on that later. So join me for a deeper look of its evolution from the first prototype and how it works today.
Buckle up!
Welcome back, factory owners. We all know cats love laser pointers and ours are absolutely insatiable. I also love to automate things, but the toys available to buy become boring really quickly. They usually just repeat the same circular movements over and over again. Even worse, in many cases the toy has to be put on the ground to work, making them an annoying obstacle. So the design goal of my initial prototype was a device I could mount to the ceiling. Back then I didn't even have a 3D printer, so I started out with off-the-shelf parts meant to move a small camera via 2 servos. It worked well enough to entertain our little predators, but it could only swivel on one axis, the other one was limited to rotation only. That pretty much limited the movement to a straight line and a semicircle at the end, like a scythe. A friend designed and printed a simple contraption for me in which I could fit the 2 servos. With that, movement on an XY plane was possible. It was also time to progress from a breadboard to a soldered board. If you know a bit about electronics and servos, you might be able to spot the big mistake I made with this early design. The software was still hard-coded back then, and I went with 5 minutes of playtime every 4 hours. It worked well for months, but then for some mysterious reason the Arduino died. I replaced it with another one, which also worked fine for a few months. Once is by chance, twice is a coincidence, 3 times a pattern. I didn't want to fry another Arduino though, so I did a bit of research and it turns out servos can draw a lot of current, way more than the Arduino can handle. The reason it worked for quite a while is the movements are slow and steady, keeping the current at acceptable levels. Every time the servos were activated though, they did one rapid movement. This must have warned the Arduino at a slow and steady pace until failure. The solution was to add a USB connector to the design and power the servos directly from a 5-volt power supply. Around that time I also got my first 3D printer, so I decided to create my own motion system with a smaller footprint. Back then I used a software called DesignSpark, which is actually a pretty cool and underrated CAD tool. Turns out they have switched to a subscription model for certain features though, so I'm glad I switched to Fusion 360. If you want to get into Fusion as well and don't know where to start, follow the link in the description to get a free introduction. Gatoino, which didn't even have a name besides cat laser back then, remained in that state for a few years and did its job as intended. The servos I used were a bit of a double-edged sword, since they either broke pretty fast or went on to work for years. I bought a pack of 5 back then, of which at least 2 still work reliably today. I bought more of those servos in early 2023 and noticed a huge difference, although they still look the same on the outside. Not only did the electronics change and look noticeably cleaner, they've also gotten relatively silent, especially compared to the ones I had from years ago. The reason I picked up on the idea again was a friend who asked me to help him with the code of his microcontroller project. I know code, but he knows way more about electronics than I do, so he showed me how to wire up an OLED display, buttons and MOSFETs properly. He was working on a Halo-style bullet counter for a BB gun, but since I don't want to suffer the same fate as the 3D print general, I won't go into further details. Anyway, the project needed a user menu for configuring different settings, and that was exactly what Gatoino needed as well. I wired up a new prototype controller and went on to implement a simple user interface and also remodeled the whole code for it to be able to respond to user input while the laser is running. Before, it was basically just running a loop and doing its thing until it was time to stop with no way to interrupt it besides cutting power. I've reworked it to use the async timer library so I could schedule every movement step with a timer. That also made it easier to control X and Y movement independently. If you want to learn more about the library, I'll add a link to that video. My friend also showed me how to design my own custom PCB and order it from JLC PCB using their software EasyEDA. They offered to sponsor me as well, and I offered them a quick shout out, but they wanted me to sacrifice over half a minute of this video, so I passed. However, we agreed on an affiliate link where I earn a small commission in case you want to support the channel. The quality has been really great so far, and I ordered all these boards with my own money way before I even thought of creating this channel. They also handle customs for you, at least here in Europe. While I was designing a professionally looking PCB, it only made sense to redesign the whole motion system as well to make it fit into a compact case. My first attempt was to simply make the whole servo assembly as small as possible while keeping the original idea of the mechanism. The outer servo moved the inner servo and the laser was attached directly to the inner servo. But as it turned out, there are multiple issues with that approach. The obvious one is that the cables are constantly stressed from being moved around. This is not a huge issue, but it will wear them down eventually, especially in a small case with tiny bend radii. Another thing is this design is limited by the servo size, so it was still rather big and clumsy even after a lot of optimization. The whole assembly needed a lot of clearance for movement, and so I would have needed a case with a lot of empty space inside. I needed a totally different approach and embarked on a bit of online research. I stumbled upon a website which explained how laser projectors work in detail. In essence, they use two mirrors mounted to a so-called galvo motor. These motors move extremely fast and precisely, but they also cost $100 each. I wasn't planning on dropping that much money on this project, but I also didn't need the extreme movement speed of a projector. I could move those mirrors using servos, so I did a few test prints to evaluate the idea. Obviously, mirrors do reflect lasers, so the fundamental physics are set, but there are a few key differences compared to a projector I need to work out. For one, projectors operate at a few meters distance from the surface they're projecting onto, while Gatoino needs to work even if you put it on a low sideboard. That meant I needed a greater range of movement for the mirrors in order to cover a large area with laser movement. Another minor detail is that projectors use highly polished metal surfaces for their mirrors, which makes for a better reflection, but those are also rather expensive. I wanted to use generic glass mirrors to stay budget friendly, and besides, cats really don't pay much attention to the reflection quality of the laser. One thing that is important though is that I had to make sure that the laser hits the lower mirror onto the top surface and not the side of the glass. In my first attempts, I naively arranged the laser and mirror in a way that it would hit the center of the reflective coating of the mirror when it's at a 45-degree angle. That resulted in deflection from the edges of the mirror's glass at shallower angles. I fixed that by aiming the laser at the outermost edge of the mirror's reflective backcoating. I also switched from using a cutout piece from an old mirror to ready-made pieces meant to make mosaic mirror art. Those also have a thinner glass layer, which is perfect for this application. The new motion system using mirrors was set. But that also meant I needed a new way to fit the servos in. Mounting them directly to the mirrors wouldn't work out. I needed a way to transmit the motion from the servos to the mirror axis. The first thing that comes to mind if you have any experience with RC cars, planes or boats is using a lever arm made of metal wire. The issue with that is I couldn't find standardized parts I could integrate. Plus levers take up a lot of space. Another option I considered was using rubber belts. In combination with different wheel sizes, that would have also made it possible to get finer movement out of the 180 degrees those servos can turn, since it only takes about 50 degrees in total mirror movement. But from watching TechMoan's channel, I learned one thing. If something is broken in old hardware, it's almost always the rubber belt. I didn't want to include something that is guaranteed to break over time that isn't absolutely necessary. So I thought, why not just use 3D printed gears? The idea was so simple I couldn't wrap my head around why it took me so many complicated approaches to come to that conclusion. For the most part, the approach was straightforward. Put a small gear on the servo and make the one on the mirror around 3 times as big to get a 3:1 ratio. For the small lower mirror, a circular gear was perfectly fine since it wasn't anywhere near the outer edges of what I called the laser cage. But for the larger upper mirror, that would have meant a lot of extra space would be needed inside the case with no added benefit. After all, over half of those gears won't ever be used with a servo moving only 180 degrees maximum. Once again, it took me way longer than I'd like to admit to come to a conclusion. And then it wasn't even my own idea. A friend gave me a push in the right direction. If I don't need a full gear, why not make it a partial gear? To be precise, I ended up with 1/6 of a gear. I also needed to make the gear's teeth wider than its center in order to make it match with the servo's position. As always, my goal was to have everything 3D printable without any supports, so I attached those gears with a hex connector to the mirror axis. This makes printing the parts very easy. For the partial gear, I also added tiny arrows to indicate in which position it needs to be attached to the mirror axis. With the gears attached, it is mounted using readily available M3 screws. The mirror itself is simply glued onto the axis. The servos, for their part, already come with the necessary screws to mount the gears and attach them to the frame. The laser then just needs to be pushed into the frame far enough for the cables to not stick out. A small channel allows for easy cable routing. Initially, the compartment for the laser was quite a bit shorter than the final version. I needed to make it longer so that the laser isn't visible when looking from the side. Now I was ready to design the case around the laser assembly. At that point I was pretty confident that there's not much else I could do to make the motion system any more compact. My first idea was to design two symmetrical halves and have a hidden seam in the middle. I didn't have a finished plan for the electronics yet, and the initial idea was to just slide them in later on. When I started to create the two halves design, I realized that it also meant I needed to screw them together right in the middle. Most Allen wrenches aren't that long, and using the ball end on such tiny screws often doesn't work well. So I went from two halves to a full case on one side and just the lid on the other side pretty quickly. This also made closing the case easier, since the laser cage is meant to sit inside a frame on both sides, which would be quite hard to fit in with the former design idea. For my slide-in electronics, that also meant I'd have a rather flimsy but pretty tall wall about 10 mm wide. This would be a nightmare to print and rather error-prone. You can see in this prototype that it already broke off. It would also interfere with adding acrylic glass, but my past self wasn't even at the point of thinking about adding a window. As you can see, I was still using a hand-soldered board at that time, so I needed to figure out how I could integrate the electronics and such negligible things as the power connector and switch first. I had designed and ordered the first PCB, but while they were in transit, it was already clear it wouldn't integrate that well into the printed parts. Didn't matter, it was my first PCB ever and I didn't even know if it would work. Turns out it did work, but nonetheless I needed to do a second revision. For one, to have the design of the PCB and case go hand in hand, and the second reason was that the laser was limited to a fixed brightness using a resistor. Instead, I wanted to use the Arduino's PWM to make the brightness configurable via the menu. I also wanted to cut the power for the servos while in standby. They were responsible for over 80% of total standby power consumption, so I integrated two MOSFETs, enabling the Arduino to shut them completely off. In reality, power consumption was now so low that my power bank didn't even recognize the load in standby anymore and shut off. It's still possible to do a manual start though. Power consumption is high enough while the laser is on. Now that I gained some experience in PCB design and knew what I needed, I did a second attempt and did a case mount first. I decided on making the front plate for the electronics a separate part that's mounted with screws. By printing that part flat on the bed, I gained a lot of design freedom that would not be possible in a single part case. At least not without many compromises and tons of support material. It also meant the bed texture is facing the front instead of layer lines, which I think looks really nice. Since the software was already programmed to use 4 buttons, I went with a Game Boy style directional pad. It's easier to print and assemble than 4 individual buttons. The display got a chamfered frame and the distance bracket for the PCB to make sure it always stays in place. To prevent flexing when buttons are pressed, I added 2 additional screw terminals in the middle. The new front plate is a bit larger than my initial PCB design, so there was still plenty of space for additional holes. I designed and ordered another PCB and it didn't fit. I made a tiny mistake in the PCB's button position. They were off by a few millimeters. As a temporary fix, I copied the front plate's design file and adapted it to the PCB for a test run. Changing the design permanently was no option, since the directional pad is vertically aligned with the center of the screen. I'm a practical guy, but I still care about aesthetics. Apart from testing the newly added MOSFETs, I could then go ahead and tweak the tolerances for the button D-pad. Luckily, it's fast and easy to print a bunch of prototypes. I can only imagine how time-consuming that step is with injection molded parts. I was really happy to see that the position of the USB-C port and power switch were already spot on. The USB port perfectly mates with the screw-on cover and sits ever so slightly below the surface. The power switch gets a little printed part on top to make it color match the rest of the case and also to have it stick out far enough. Even though I did a lot of measuring beforehand, I didn't expect it to fit that well on the first try. But regardless of that, the PCB design for the USB port needed to change. The part I used had tiny surface mounted pins that are rather finicky to solder. Meanwhile, I found a design with just 2 through-hole pins for 5V power, which is way easier to solder by hand. I also added a small capacitor to stabilize the Arduino's power supply. It worked fine in automatic mode, but there were some occasions when activating the servos caused fluctuations and crashed the Arduino. So with these few changes, I was ready to order the next batch of PCBs. This time, everything fitted as intended. The device was now fully functional, but having a huge opening in the front means everything inside is rather vulnerable. It also made it look incomplete and unprofessional. Surprisingly, dust isn't a big concern. Even with the early prototype running for months, the mirrors didn't collect much of it. Nonetheless, it needed a front window. I opted for 2mm thick acrylic glass since it was easiest to fit into the existing designs. I just needed to extend the front a tiny bit and add a little frame in. After a bit of experimenting, I also added 2 angled brackets to the electronics plate to keep the window from sliding down. Initially, I planned on using red acrylic glass to hide the inside of the machine while still letting laser light shine through. Surprisingly, it was pretty hard to find 2mm thick sheets in red. Thicker material would have meant I needed to do more adjustments to the case, and upon closer examination, I also liked the look of the clear sheet. It's really mesmerizing to watch the mechanism move. For the first prototype windows, I used a table saw and the edges were pretty rough. Luckily, the frame hides those edges completely. What I didn't like was the cables of the servos that were visible at the bottom of the window. I couldn't just extend the front plate since it would need to be at an angle, and that means it can't be printed flat anymore. I figured the bottom part of the window doesn't come in contact with the laser at all, so it doesn't need to be transparent. I wrapped the window with a bit of electrical tape to see how it looks. The servo cables were now invisible, which made the overall look yet a bit cleaner. Around that time, I got myself a cheap Chinese CO2 laser cutter, which not only enabled me to cut the windows with great precision, I could also engrave that bottom part to make it a bit opaque. A bit of sandpaper and painter's tape can do the job just as well, but playing with lasers is way more fun. I also thought about adding the logo to the window, but settled on having it imprinted to the front plate. The hardware design was now pretty much done, but there was still one small thing I wanted to optimize. I initially planned to make the wall holder and add-on to be screwed onto the back. Since the case is printed on its side, I thought this would be easiest to print. Now it came to my mind that by integrating one single perimeter of support material into the design, I could make the common keyhole design for screws work while maintaining easy printability. Those keyholes need a lot more space, but there was still plenty left inside the case. At some point I already changed the former design from a solid block to a floating bar for better cable management, which I also kept for the new keyholes. If you pull the servo cables straight down, there's a chance they could touch the moving gears, which is prevented by this cable guide. While the hardware design took place, the software was also under constant development. As of making this video, Gatoino supports customizing the play area to accommodate any placement and room size, minimum and maximum movement speed to satisfy cats of all ages, adjustable laser brightness, optional laser blanking, that means it turns off the laser briefly for additional confusion while playing, customizable play session duration, and customizable sleep time until the next run session. The automatic timer can also be turned off completely, and a manual start is possible at any time. Let me give you a quick demonstration of how all of that works. After you turn on the device, it will show the splash screen, and after the splash screen disappears, the device is basically ready. So right now, the timer is already running in the background, and you can start a manual play session at any time by pressing down, and it will just run for the duration you have set. And you can also stop it again by pressing down. And you can also enter the menu by pressing up. And just to show you, if you activate the device beforehand, you can also enter the menu and it will just stop. And with the first menu option, next run, you can see when the next run is scheduled, if you're keen to know when the cat will play again. And you can also restart at sleep time. If you go back now, you see it has been restarted to 6 hours. That's what I've set. And in the timer settings menu, this is the first one where you can make settings. You can set the timer on and off. When you turn the timer off, it will tell you there's no timer set when you ask for the next runtime. In the menu here, you can set a runtime and you can set all those values separately. That means you can set the minutes first and then the seconds. And every time you press up, you will advance to the next number. If you press down, you go to the last number. And if you press down again here, you will see it will not save anything. If you enter again, it will still say 5 minutes. And if I enter again, I press enter 2 times, then I have 6 minutes. So this value is saved when I press up. The same goes for the sleep duration. Here you can set days as well. And that's basically everything for the timer settings. Now for the laser settings, you can adjust the brightness of the laser. I will leave it at max value for the video's demonstration. You can set the limits. It can travel to the left and the right. Because we're on the shelf directly, the limit is now pretty much at maximum. And also to the right, you can see when I change the value, it will travel more inwards. Of course, if you put it on a shelf and let it shine to the ground, it will cover a way larger area. Same goes for near and also far, where the shelf again is a limit because it's too shallow. And you can set the speed value, minimum and maximum, to a value between 1 and 15. If I set minimum to 1 and maximum to 15, you will see a huge variety in playing speed. It will randomly choose any value in between. With the Show Boundaries option, it shows you how large you have set the play area, and you can also check if it is colliding with any of your furniture. Notice that the shape is trapezoidal, means it gets wider the farther it is away from the device. There's no keystone correction like with a projector. There is currently no real-time clock, so you can't just set a specific time of the day. It will always sleep for the given amount of time. That also means starting a run manually will reset the timer. This behavior was always fine for me and also for our cats, since you never know when they get their half hour of power anyway. If enough people are interested, I might add a real-time clock in the future. I can also imagine upgrading it with Bluetooth and integrating it into smart home systems like home automation.
Everything is better with Bluetooth.
My initial idea was to build, sell and ship Gatoino myself. Unfortunately, that makes me a device manufacturer by European law, which means I need a license to comply with electronic waste recycling. I even applied for such a license, but not only did it take them 4 months to even bother to check my application, I also made a formal error, which means I got rejected and need to apply again. Not to mention I still paid for that application. But wait, there's more! This license is only valid for one single country, so I'd need to apply for all countries I want to ship to. There are ways to get around this if you're selling a kit that's not a whole product in itself, but I'm not sure what falls in that category. If you follow CNC Kitchen, he recently showed a filament extruder which you have to assemble yourself and is sold without a power supply. He said it's for legal reasons. I'm 90% sure this was to fall into that category, why else would you leave out a power supply? Stuff shipped directly from China doesn't face those issues, since the customer who bought it is responsible for the import. Okay, rant over. Nevertheless, in my opinion, Gatoino is way too cool to only entertain our own micro tigers. According to statistics, there are over 370 million cats kept as pets worldwide. More than 20% of households own one or more cats in most Western countries. They all deserve to have some fun, so I'm offering the build plans, PCB files, the software and 3D printing models, including step files, as one package for sale as a way to support the channel. The software is open source as well. Last time I checked, the cost for all the materials needed were around $35, including the PCB and self-printed parts, if you get them from AliExpress. But you can also source them locally. All parts are pretty common. You might even have a few parts like resistors and pin headers already lying around. Gatoino makes for a very beginner and family-friendly project. The necessary steps from soldering to flashing the software are explained in great detail. I hope you liked the project and this slightly longer video. Let me know your thoughts in the comments. In any case, you can subscribe over here and watch another one over there, and get ready for some more cat laser action in the outtakes. See you in the next one.